second of the 14-part Microsoft SQL Server 2014 launch webinar series. Over the coming weeks, the past virtual chapters will be hosting various Microsoft speakers from the engineering and technical marketing teams. They'll be discussing new functionalities and enhancements in SQL Server 2014. Before we get started today, I wanted to share some information about PASS and tell you a little bit more about the DBA Fundamentals virtual chapter that we run, and tell you a little bit about one of the future meetings that we have. So let's go ahead and get started. So for those of you who might be new to the DBA Fundamentals virtual chapter, let me take a moment to introduce you to the PASS Association. PASS is an independent, not-for-profit organization run by and for the community. PASS's membership is growing with more than 100,000 members worldwide. The organization supports data professionals who use the Microsoft Data Platform to connect, share, and learn through the virtual chapters, offering free online training such as this one, in-person events including the PASS Summit, Business Analytics Conference, and regional events including SQL Saturdays and SQL Rally. You know, there's a never-ending list of things you can do if you want to become connected to the PASS community. So I really encourage you to visit the PASS website at sqlpass.org to find out how you can become involved and find out more about what's going on. So as a valued member of the DBA Fundamentals virtual chapter, we're extending a $150 discount to the PASS Business Analytics Conference taking place May 7th through 9th in San Jose, California. Just use, please, the discount code BA Victor Charlie 09 when you register. This conference is going to offer over 70 sessions by the world's top business intelligence and business analytics experts, and over 20 hours of networking opportunities with 1,000 data professionals from around the world. You really don't want to miss it. You'll walk away with, you know, some real-world insight from companies. I mean, we have companies like Microsoft, Wells Fargo, SurveyMonkey, Yahoo, and Intuit, as well as best practices and prescriptive guidance and strategic vision. I really highly recommend you find out more today. So check out passbaconference.com. One more time, that was passbaconference.com, and when you register, again, you'll get a $150 discount by using the discount code BAVC09. So again, my name is Mark Swafford. I'm the chapter leader of the DBA Fundamentals virtual chapter. If this is your first DBA Fundamentals meeting, please, join us again. We typically have our meetings the first Tuesday of each month at 11 a.m. Central Standard Time, and all meetings are recorded and archived for future viewing on our website. Our next meeting, which is April 1st, I believe, and this is not an April Fool's joke, it will be, the topic is, so you've installed SQL Server, so now what? It'll be a great presentation. It'll be presented by Joseph D'Antoni, and you can go to the Fundamentals virtual chapter website for more information, and there will be a link there to register as well. So all of our topics for the DBA Fundamentals VC are geared toward, typically DBAs in their first year or two on the job. What we try to do is just try to build a good foundation for DBAs all across the world to build on later in their career. So we offer a lot of level 100 topics, and quite frankly, we have some of the best DBAs in the world that present for the chapter. So it's really good stuff. If you're not a member, I ask that you just check us out. So that's really all the housekeeping I have. Just one more quick thing. On your GoToWebinar menu, you should see a little hand, and if you have any trouble hearing us, or you have any kind of audio or video difficulties, or need some help, just hit the little hand button. What that'll do is it'll raise your hand, and we'll try to come to your aid. And we'll try to help you with those problems. Another thing you should see is a chat window, or a question window, sorry. And you can, during the presentation at any time, you're welcome to ask questions, and we'll try to field as many questions as we can about the presentation as we go along. And if we have time at the end, we'll field some questions then as well. So without further ado, I'd like to introduce everyone to Kevin Farley, who is going to share with us our topic today, which is SQL Server 2014 InMemory OLTP. Kevin, I appreciate you being here, and thanks for giving the presentation to the group.
Thank you. My name is Kevin Farley. I'm a Senior Program Manager in the SQL Server product team. And for the last 2.5 years or so, I've been working on what started out as the Hackathon project. It came to you as InMemory OLTP. And that's one of the features in SQL Server 2014, which we are just in the process of releasing. Pretty exciting time right now. My background: I've been with Microsoft for about 8 years. Prior to that, I've worked in a number of different industries, going back and forth between the database world and the storage software world. So I've kind of had my hands in both of those areas of technology, and that's the niche I've worked in at Microsoft at SQL Server. So without further ado, I'm going to talk to you about the InMemory OLTP feature in SQL Server 2014. Before I get with that, let me set kind of a context about SQL Server 2014 and where we've made investments in the product. The investments in 2014 have been a little bit more targeted than they've been in previous releases. In previous releases, we've tried to make sure that we delivered new functionality across the entire suite of features within SQL Server. Starting with 2014, we've been more targeted. Instead of going broadly and shallow, we're going really deep in a few very targeted areas. And part of that has to do with having a shorter release cadence, and part of it has to do with taking on additional work in the cloud with the same number of engineers. But the main focus there is, the main message is, this release we're focusing intently on these technologies. The next release we will probably invest some in these technologies and some in other areas. So if you're an area that you care about didn't get new features in this release, it doesn't mean we're abandoning it. It just means that in this particular release, that's not one of the areas we invested in. The next release it may be. So where did we invest in SQL 2014? The main areas are the in-memory technologies, and in-memory OLTP is just one of those. In-memory data warehousing, which I'll mention briefly in this talk, can give you huge gains. This is related to the Vertipack technology that allows you to use Excel as a front end for a huge data warehouse, and it's an evolution of the Columnstore technology that was first introduced in SQL Server 2012. Now you can update your Columnstore, and it's the clustered index, which has some really nice features. Gives you huge compression, for one thing. SSD buffer pool. Again, I'll go into that in a bit in the next slide. Has some interesting advantages. The high availability space, we've done some more fit and finish in the always-on area. So there's a number of scenarios where previously you would take a node offline, particularly readable secondaries would go offline as a response to certain events. And we've gone through those and greatly reduced the number of events that will cause a loss of availability of a secondary node. And also online database operations, where we're constantly going through the engine and increasing the number of operations that can be done fully online without taking your database offline. One of the new areas of investment is the hybrid scenarios. So we're doing a number of scenarios where we're crossing the bridge between your on-premise deployments that you're used to and deployments that touch the Azure cloud world. Backup to Azure is one where you can easily set your system up to do your backups directly into Azure storage, and there it's held triply redundant, it's encrypted, it has a lot of nice benefits. So instead of doing your backups locally and sending it off to Iron Mountain or something, in this case you can just send it directly to Azure and let that be your vault. HA to Azure VM, so we give you the ability to set up an availability group where one of the replicas is running in an Azure VM. So even if your whole data center goes down, you've got a replica that's still up and running in our data center. Deployment to Azure, we've made that simple. There's just a wizard you click through and deploy your replica up to Azure that runs the whole process through from creating your VM all the way through to getting it joined into your availability group. Other investments, we've done work to be better together with Windows Server. So with this release, we now support the REFS file system that's new in Windows Server 2012 and beyond. REFS is a new file system that replaces NTFS. It's very, very similar, but the implementation has been reworked to be much more scalable, robust, and performant. You can now online resize VHDX disks in a Hyper-V environment, and we obviously support Windows Server 8.1, codenamed Blue. PowerView has also been expanded, enabling it to use existing analytic models and new multidimensional models. So this talk is all about the in-memory technologies. So I'm going to focus in a bit more. We've got all these different technologies. How do you compare and contrast, and where do you use each one? InMemory OLTP, which will be the focus of the bulk of this talk, is applicable to transactional workloads. So what do we mean by that? An OLTP system is typically characterized by transactional workloads, concurrent data entry. You have a bunch of different users or threads hitting the database at the same time, processing and retrieval. Typically the queries that you see are fairly short-lived, going after a specific number of rows rather than broadly scanning a whole table. So it's not so much for reporting as it is for record keeping and keeping up with very fast operations. In-memory data warehousing, by contrast, is more to support the analytics world and data warehouse type queries, where you have decision support workloads, large scans and aggregates across very big volumes of data. And it's not uncommon with the clustered Columnstore to get upwards of 80 to 90% compression. So you can drastically reduce the resources, both memory and disk, that are required to house a considerable volume of data. And when we reduce the volume, it also significantly reduces the time it takes to get to your data. You're not transferring as many bytes from disk to memory. You're not scanning as many bytes in memory. Everything just goes faster. It's entirely architected for that data warehouse workload. Finally, SSD buffer pool extension is an interesting feature, kind of crept in at the end of the release. What it is we give you the ability to define an area on disk, and obviously the recommendation is that that would be on a fast disk like an SSD. You define an area on that disk that acts as a secondary cache to the buffer pool. So what we put there are pages that are clean, that don't need to be written back out. So the clean pages get cached when they get evicted from the main buffer pool. That way they're in a fast to access, fast cache in case we need them back. And we've done some work to try and predict what pages we think are most likely to be reused, so we don't cache the results of large scans. Again, this is a feature that's targeted more towards OLTP workloads. So if you do a large scan across an entire table, we're not going to cache those pages because it would just flush everything out of the buffer pool storage. But if you're doing a bunch of point fetch, we'll try and keep those pages in. If we can't keep them in the buffer pool directly, we'll keep them in the SSD buffer pool extension for fast retrieval in case we need those pages again. As a result of some of the feedback we got from customers, originally the buffer pool extension feature was targeted at enterprise customers. We got a lot of features that it would be far more useful in standard class environments, so it has been reclassed as a standard edition feature. So SSD buffer pool extension is available in standard and above. It allows you to effectively multiply your RAM. So if you don't have enough memory to keep the interesting hot set in memory, you can extend it using the second level cache. Just as a sidelight, since I was on the topic, the other significant change to standard edition that has been made with SQL Server 2014 is that we've doubled the amount of memory that it can use. Previously, the standard edition was capped at 64 gigabytes, and with this release it goes up to 128. So, getting on to the heart of this talk, why InMemory OLTP? Hackathon is what the project was codenamed. It started a long time ago, and we needed some way to describe it before we knew even what the shape of it was going to be. The SQL Server team stepped back and made some observations, primarily that most database management systems on the market, the traditional relational database engines, were designed around some fundamental paradigms that were just always true. One of them was there's one type of database engine. There's not a set of specialized engines out there. There's one type of database engine, and whatever you need to do with the database, you do with that engine. The other paradigm that was observed is that memory's very precious and very limited. So the database systems are designed to handle the case where you can pull a small set of your data into memory, manipulate it, and then it's going to get evicted to make room for other data that you need to access because you can't hold it in memory all at the same time. So this started about 5 or 6 years ago. The team was spun off to just step back and do some thinking in terms of, if we were starting to think about a relational database engine now, with none of that history, what would it look like? That was the genesis of the InMemory OLTP feature. That group of people went off and tried a bunch of different approaches, saw some that were bearing fruit, looking very promising, and that then became productized and integrated into SQL Server. So the resulting feature, InMemory OLTP, is designed around being high performance. That's obviously the key value proposition, is it goes fast. It's a memory optimized OLTP engine, and that means that's very specifically it's optimized for keeping your data in memory, and it's also optimized for OLTP queries. It's not going to make every workload faster. It's not going to make data warehouse queries faster. It's going to make OLTP queries faster. It's tightly integrated into SQL Server. That's a huge differentiator. All the other in-memory offerings I've been able to find on the market are separate products. You have your OLTP engine, and you've got your data warehouse engine, and they're different. And it's architected for modern hardware trends. So let's dig into the hardware trends a little bit deeper here. A couple trends that we noted. One was on the processor side and one was on the memory side. On the processor side, Moore's law obviously shows that the complexity, as measured by the number of transistors on a chip, has been doubling every few years, and that continues. That's the green chart that goes out there. What hasn't continued is the clock rate. Shortly 2003 or so, the clock speed of the processors leveled off at just above 3 gigahertz, and it really hasn't moved much since then. You occasionally see a processor slightly over that, slightly under that, but that's really where it stalled. And that made a big change in the way software works. It used to be that your next release of your product would just go faster because the clock speed of the CPUs was faster. So a single-threaded app was going to go faster on the next generation of hardware just because the hardware was moving bits that much faster. That's no longer the case. So where did those extra transistors go? So we're delivering much more capable CPUs, but they're not going any faster. What's happening is that we're now delivering more and more CPUs per chip. It used to be single processors were the norm, dual procs were pretty cool. Now you're seeing 6, 8, 10 cores per chip. Putting those two together, that means the way that you get the power out of modern generations of processors is by running workloads that are very highly parallelized. So you have to build your application code in order to take advantage of that and do a much higher degree of parallelism than was the case previously. So that's on the processing side. On the memory side, it's been true for a long, long time that the cost per gigabyte of memory has been dropping. That's nothing new. But there's been a qualitative shift that's happened in the last, 5 or 8 years. And that's that the amount of memory you can reasonably get in a commodity server machine has significantly changed. And what that does to the amount of an interesting data set you can keep in memory has shifted dramatically. And the example that I use is about a year ago or so I spec'd out and purchased a server for our team to use for demos and also for performance investigations. And that server has 2 sockets, 4 physical cores per socket, 8 logical cores if you count hyperthreading. So 8 logical processors. It's got 256 gigs of memory, 4 SSDs, and a number of spinning drives for bulk storage. And that's a $13,000 machine. So again, this isn't targeted at the $1 million appliance market anymore. This is looking at what we can do with relatively commodity machines. That means we can keep a really interesting amount of data in memory all the time without running out of the memory that you've got. So this is kind of the core of the explanation of what in-memory OLTP is. And I spend quite a bit of time on this slide. If you have questions, I will try to take them at the end. I'm going to reserve ideally at least 10 minutes at the end for questions and answers. If you have a burning question, put it in the chat window and I may be able to get to it in line, but in general I want to get through the material and then we can have a discussion afterwards. So about the way this slide is laid out in pillars. We have customer benefits across the top. So you want high-performance data operations, efficient business logic processing, frictionless scale-up, and a hybrid engine and experience. On the bottom, we have the hardware trends and business drivers that this is recognizing. And then we have the features that we built into this product in order to realize those benefits and recognize those trends. So going left to right, we have the hardware trend of steadily declining memory price and increasing capacity in a commodity server, and the customer benefit of high-performance data operations. That has translated into main memory optimized pillar and value here. What that means in SQL Server is tables that are declared to be in memory are optimized for in-memory data. So the data structures that we use internally for those rows and in fact on disk as well, are different from the data structures we use in traditional tables. Just as Columnstore uses different physical representation than traditional tables do, in-memory OLTP tables are physically different, and in memory they're significantly different than traditional tables, and in particular they're specifically optimized for in-memory data access. The indexes function differently. We have non-clustered indexes which are optimized for range queries that are a modified B tree. They have a lot of the characteristics of a B tree, but they have some nice characteristics in terms of concurrency, in that there is no locking. So if you ever have the case where you're having page splits that lock whole sections of the B tree, that doesn't happen with these indexes. There's no locking. Hash indexes are a new style of indexes that we've introduced with in-memory OLTP, and for exact key lookups they're extremely fast. So what does the storage look like? Each row is represented as just the native representation of those data types in memory. So there's a block of memory for each row allocated. It's got a header that has some timestamps for when the row was created, when it became no longer visible, so in other words when it was deleted or when someone has replaced it with a newer version. We never modify these rows in place. We create a new copy of the row in memory, and new transactions just see the new version. I'll get into that concurrency model a little bit later. But the point is, we're not embedding this within a page structure. It's just that row in memory. So page structures are an artifact that was used for facilitating taking subsets of your data from disk into memory and pushing it back out to disk again. It's a container for a set of data to move back and forth rather than managing each individual row and where it went on disk and all that. We use pages for that, and that's much, much more efficient. So if you've ever had a workload where you're, say, loading a table with a constantly ascending clustered key, you run into page latches if you're doing this multi-threaded. So what that is even if there's not a collision on specific values, on specific rows, you have multiple rows getting inserted into the same page, and we have to lock the physical page to keep it consistent as it's modified. That situation doesn't happen here because we don't use pages. So it's much, much faster. Because each row is available in memory, we can very efficiently implement hash indexes. Hash indexes are where you take your set of whatever columns that you define to be your hash key, you take the values in your query, we run them through a mathematical hash function, and that gives us an offset into an array of pointers called hash buckets, but they're just an array of pointers, and each pointer takes you directly to the row or rows that match that key. So a lookup in a hash index is just a pointer dereference in memory within the context of the engine, as opposed to a B-tree scan where you start at the root of the B-tree and you jump from page to page going down the tree until you get to the leaf node and then find your row. And at each stop, you're getting to a database page where you have to crack the page header, interpret the structures, find your position in the slot array within the page, and interpret that structure, and then that takes you to the next hop. It's just far, far less processing that we have to do the lookups. So that's why this engine is very, very efficient for exact key lookups. If you're doing a range, hash indexes just don't work for that because you're going to end up scanning every bucket in the hash array to find your records. One of the artifacts of using the hash function, its job is designed to spread rows as evenly as it can across whatever range of hash buckets you've given it. So that's not going to be ordered. There's no implied ordering at all in a hash index, and there's no physical ordering as well. So we've got this data that's in memory all the time. What if I want it back after I reboot my system or after it crashes? This data by default is fully durable, and that means that as we create a new version of a row, whether it's an insertion or an update, that change is logged in the transaction log along with all the other changes for that transaction, which may be done in traditional tables, or it may be done in other in-memory tables. There's a background thread that takes and finds those hekaton rows in the buffer before that gets written out to disk from the log buffer, and copies them into a set of sequential files we call checkpoint file pairs. So the nice thing about that is every change before the commit is acknowledged is hardened in the transaction log, so it has the same durability guarantees that the rest of SQL Server does. But unlike the rest of SQL Server, when it gets written out to disk, it's a pure sequential write pattern, which is generally the most efficient pattern you can get for writing to spinning drives. So we're making the most efficient use of the hardware we can. Those checkpoint files are only read at database startup time when we pull all that data into memory. So that's the advantages of main memory optimized. This is not pin table where you can just force the pages to stay in memory, because we don't have pages. It's entirely different memory structures. So that's recognizing the additional memory you have to work with. In order to compensate for the stalling CPU clock rate, we want to get the most benefit out of every CPU cycle that we possibly can. So we have the concept of natively compiled stored procedures. What that is if you have a stored procedure which only references memory optimized tables, and they can't talk to traditional tables, but if it only talks to in-memory tables, you can decorate the procedure definition with natively compiled, and what that causes us to do is at stored procedure creation time, we take the T-SQL, optimize it through the standard SQL optimizer, and then we translate it into C code and compile it using the VC compiler, which has its own optimizations, and that creates a DLL which is loaded into the engine. So that means execution time for one of these natively compiled procedures, instead of being a set of interpreted T-SQL statements where each one has a number of context switches where you're interpreting the T-SQL and finally getting down to the access methods which find the data wherever it lives. It's just a function, call it engine context. The result of that is that there's no context swaps. Once your transaction starts, it's going to complete. Makes it extremely fast. In SQL Server 2014, not all stored procs can be readily translated into natively compiled. There are some constructs that need workarounds because we don't have quite the full surface area that is being addressed in the next version. But when you do have a stored proc that can meet those requirements, it's highly beneficial. So the next pillar is frictionless scale-up. So we said that in order to take advantage of the modern processors, you have to enable your applications to run much more highly concurrent than was previously the case. But if you do that in traditional database engines, you run into locking and you run into latching, which slows you down and prevents you from making use of your CPU resources. The hekaton engine, as I said, when you update a hekaton row in-memory OLTP table, we don't update the data in place. We create a new copy of the data, and that's a multi-version concurrency model. This system uses optimistic concurrency, which says, pessimistic concurrency says, if two people want to access a row, I'm going to guess that they're going to conflict some way, and so I'm going to prevent the second access from happening. I'm going to just make it wait until the first accessor is done. And there may not have been an actual conflict, but that one's going to get stalled anyway. Optimistic concurrency says, well, in the majority of times, there wouldn't be an actual conflict, so I'm going to let both of them through. If it should happen that two transactions try to modify the same row within the same time frame, the second updater will be failed and have to retry. That's in operation outside of a few pathological or extremely difficult scenarios. That retry scenario is quite rare. What that gains for us is that the whole Hackathon engine uses lot-free algorithms. So there's no part of the Hackathon engine, the InMemory OLTP engine, that uses lots. There is no lot manager within the InMemory OLTP system. There's no latches because latches are there to protect pages and we have no pages. There's no spin locks. All that is done to allow multiple threads, lots of threads, to go concurrently at full speed without ever getting stalled. So that means where you may have had only a few threads executing at any point in time, all of your threads will execute. It also means that it's really expensive to take a thread that's executing, stall it, have it get destaged, and then have to reestablish all of its context when it comes back into runnable state. That generally doesn't happen. So once a transaction starts executing in this environment, it's generally going to run to completion, either commit, rollback, whatever, but it's not going to stop halfway through. And that, again, greatly shrinks the window of time when there could be a potential conflict. So that's the value proposition, recognizing many core processors. Finally, the differentiator I mentioned earlier that sets us apart from most of the rest of, in fact, all of the rest of the products out there, is that this is a hybrid engine. The whole idea is this is all tightly integrated into SQL Server. It's all one database engine. There's different access methods paths for in-memory versus traditional tables, but it's all within the same product, within the same database. You can define some tables to be traditional, some tables to be memory optimized, and that's key because you may have a fairly huge database that you couldn't really fit the whole database in memory, multiple terabytes of data. But if you look at the data which is hot, which is really performance critical, it's generally a small subset of that entire body of data. So you just move those tables into memory and leave the rest on disk so they can be accessed using the most appropriate methods to access each class of data. The payback for that is not only the efficiency there, but it means that all of the traditional utilities, methods, syntax, it just works. There's a few new syntax, but it's very minimal difference in syntax. It's all within the same environment that you're used to. It's not learning a new product. It's not installing a new product. It's just part of SQL Server when you install it. This is an enterprise class. It's lit up in enterprise, but it's just fully baked into the product. Backup and restore just works. Always on just works. It's just part of the product. It also means that when you do look at migrating a database to in-memory, you can do it incrementally. If you look through your environment and find, okay, this is the hottest table, this is the one that's causing me the most blocking and the most performance problems, start by just moving that table into memory. Don't touch the code, just move it. And if that solves your problems because your problems were related to locks and latches, you're done. End of story. If removing that bottleneck uncovered another bottleneck, which is the typical pattern in performance tuning, then you can address that one. It's not a big bang here. You're not required to just rewrite your whole environment to move to in-memory OLTP. You can do it stepwise and you can control your investments. I think that's a huge advantage there. So I've done a lot of talking here, a lot of discussion of what this product looks like. Let's see in operation what it looks like. I'm going to do a demo here of creating an in-memory database, a database that contains in-memory tables, and show you what it looks like and how it performs. So I've already dropped the database from the last practice run. So I'm going to create a database. Nothing new here. Oops. Okay, well, maybe I didn't. Let me drop it. Now I'll create a database. Nothing new. Traditional database, putting data log files on the E drive because it happens to be faster than my C drive. This is one piece of new syntax. I said that there was a set of sequential files that keeps the checkpoint file pairs where we persist the data. So we now have a file group type that contains memory optimized data. It's much like a file stream file group. It is a special purpose file group, though, that only contains these checkpoint file pairs. So we're going to add that file group, and we're going to put a container in that file group. Again, for simplicity, it's in the same location as the rest of the database. You could have it wherever you want. You can have multiple containers to spread the I/O load on startup across multiple spindles, and that's highly recommended. The authorization here is just because the machine that I'm using to run this on is in a different domain than the rest of it, and it's just simpler. So I'm going to start by creating a traditional table, shopping cart. It's fairly simple. Your ID is an int column, user ID is another int, has a non-clustered index on it. Create date is the date time and your total price, money type. And I'm going to create a procedure to insert rows into that, and that just takes a starting ID and account for the number of rows that I want to insert into the table. Okay, fairly straightforward. It just does a loop. Now I'm going to insert 100,000 rows. This fancy is null select just allows me to find the highest value that's currently in the table, and if there aren't any rows, it picks one. And then that execs the insert sample carts with that starting ID and inserting 100,000 rows. So let's see that this is on a traditional table. So query is executing. This is a reasonably fast machine, so it shouldn't take too long. And again, there's no contention because this is just one thread doing the inserts. And it took us 13 seconds. Not too bad. And indeed, there are 100,000 rows there. Now we're going to see what it looks like to re-implement that table and that stored proc in InMemory OLTP. I'm going to drop the original ones. I'm going to create the table. And again, the same columns, the same data types. You'll see that the primary key is non-clustered hash with a bucket count. The bucket count says how big should I pre-size that array. The array in this release is fixed size, and you do need to have it close to the number of unique key values for it to be the most efficient. And you'll notice that all the indexes are non-clustered. That's because every index is just a pointer to the root row. So clustered versus non-clustered really doesn't have any meaning because all indexes point to the actual full row and contains all columns in the row. And you have secondary index, which is just a non-clustered hash. So the same layout, and you also see the with memory optimized equals on. I told you that the default durability is full durability. You have the option to declare the table as durability equals schema only, which means that on restart the table's there but it's empty. The payback for that is we do 0 I/O. So if you have data that needs transactional semantics but doesn't have long-term value, and the canonical example is an ASP session state cache, that's how you would do that. Make the table, and this is a native procedure, native compilation. Begin atomic is the new syntax there. The rest of it is the same. And set statistics time on so you can see how long in detail it takes to run this. And we're going to run the same call to insert 100,000 rows, and it's done. So it took 13 seconds to insert into the traditional table. It took 90 milliseconds to do the same amount of work with this environment. So that's an example of what it looks like to do this sort of, to create a table, to create a natively compiled stored procedure, and in a very trivial example, what the speed up can be. Obviously, there's a lot of cases where you're going to see differing ranges of speed up, and some where the changes are more complex, but this is illustrating the possibilities. So let's go a layer deeper into what's happening here. This is sort of a block diagram of SQL Server as it has existed for a long, long time. Starting from the top, your client app goes through the network to the TDS handler. TDS is the protocol SQL Server uses for talking over the wire or between processes. From there, it gets parsed, goes through the catalog looking up to see if that plan has been cached, goes to the algebraizer, the optimizer, and then it goes through the plan cache for SQL statements, ad hoc, as well as stored procs. From there, it goes through the interpreter for T-SQL. Access methods is the method that knows how to find pages in memory, and if the page isn't in the buffer pool, how to pull it into buffer pool from on disk and optionally invict other pages. You'll see on disk, buffer pool has copies of the pages and the indexes for some of the pages. And on disk, you'll see your data file group, which has the different tables represented, and the kind of checkerboard squares represent index data for that. And there's data in the transaction log for tables and indexes. So the InMemory OLTP engine introduces a separate area of memory. It's managed separately from the buffer pool, but under the same SQL Server memory management system globally. And there's the memory optimized table file group, which we saw. We're going to move two of the tables across to the InMemory OLTP engine. And you see that their tables moved from the table data file group to the memory optimized data file group, but the indexes didn't. Why is that? That's because since we have to read every row to put it in memory at database startup time, it's more efficient to just build the indexes on the fly as we bring the database online than it is to store them on disk and pull them back as structures. So we don't store them. That means there's no log written on behalf of any index operation, and indexes don't take up any space on disk because they're never persisted other than the metadata. So again, they're rebuilt on startup. They're materialized in memory, but not on disk. The simplest access path is where you go through the interpreter for T-SQL, and we use a subsystem called query interop, which uses the InMemory OLTP version equivalent of access methods to access the data in memory. So you can just fire regular queries at an InMemory OLTP engine, and it works just fine. Just like you saw me do the count star of the table after I had inserted it, same works. You can do virtually any statement against the in-memory tables via query interop. It won't be as fast as the optimized and compiled stored procs, but it greatly reduces the amount of work you have to do to move. Another case where you can control your investments. And you do the checkpoint and recovery I/O. The other option is to take the statements, run them through the InMemory OLTP compiler, and access the natively compiled stored procs and schema. When you define a table, we create and compile access methods to fetch the row and do the standard operations on it by default. And like I said, you can declare a table to be non-durable, in which case there's nothing logged for that table and it takes up no space on disk. Obviously, you don't do that about data you have that has long-term value, but for data that's transient, again, a cache of some form, the midpoint in an OLTP stream is another canonical example. It makes it way faster because typically your bottleneck is going to be your log I/O because we've removed a lot of the other bottlenecks. With this, there is no log I/O. So just a few slides about where we get the speed up from. I've been talking about the InMemory OLTP engine and how it makes it faster, why it's faster, why natively compiled stored procs and schemas are faster. So the part of a transaction which executes in that environment is generally going to be 10 to 30 times more efficient. It's 30 times less time spent. However, also we have reduced log bandwidth and contention because you're not doing any logging I/O on behalf of index operations. Also, we log the entire new row once rather than each modification if you do multiple modifications to a row within a transaction. Checkpoints are background operations and use sequential I/O rather than the random I/O of writing checkpointing pages out to disk in traditional tables. What hasn't changed is the networking stack and all that logic above that. Parameter passing, result set generation, all that is the same code as the rest of SQL uses, which is fine, but it means it's not specifically sped up. So if you have very narrow, shallow transactions, your application is very chatty, so you go into SQL Server for a single statement, come back out, you're going to spend as much time or more time in that top layer as you do in the whole rest of the engine. And we're not doing anything to speed that up in this release. So you're going to see far less benefit from moving to Hackathon, to InMemory OLTP, than you would if you had a significant amount of logic in a stored procedure where we can just stay down in that engine layer that's really fast and do lots of work. So generally, the more logic that is pushed down into stored procedures, the more benefit you're going to see for InMemory OLTP. Kind of moving back to a big picture, the other piece of the InMemory story is the InMemory row store and column store scenarios. So again, we have the InMemory row store as well as the updatable column store for this release. I'm not going to go through this in a lot of detail because I want to save time for questions. The row store is designed for relatively small sets of data relative to the size of a huge data warehouse. For V1, we're limiting it to 256 gigabytes of memory in memory-optimized tables within a database. Column stores are designed for much larger sets of data. We have updatable column stores on campus here running into tens or hundreds of terabytes, and very happy. Read patterns for in-memory row store ideally are key lookups, non-blocking. That's not a key scenario for column stores. They just aren't nearly as fast or efficient doing specific row lookups. Column stores are ideal for large scans with aggregates, star schema related types of joins, not so ideal for in-memory OLTP. Write patterns are ideal. It's a key point for contention-free data operations. Updatable column store is functional, but it's not its high point. Change happens to an on-disk row store and gets merged into the column store in batches. So highly transactional isn't going to be as fast on an updatable column store, but you can update it and keep it in sync with reality, which is a big improvement. So with that, I'm going to spend a couple minutes. I'm going to kind of blaze through a demo here because I think it's cool, and then we'll get to some questions and answers. So we have here order processing, our web front end for a purchasing system. This application on the right is a driver for purposes of this. It provides a background workload. It also, every action that I'm going to take on this UI gets multiplied by a factor of 1,000,000. So every time I make a choice, it simulates 1,000,000 other users making the same choice by background threads. And so we're going to start it up, start it running its background workload. We're getting 300 to 500 transactions per second. Recommendation latency is 6 seconds. What does that mean? That means if I'm a customer, I go here, select something. It's scanning a data warehouse or scanning a bunch of tables to figure out if a customer chose this title, what are other titles that might be good prospects. That takes about a little over 6 seconds. If I want to buy that title, you really don't want customers sitting there waiting. This is 3.5 seconds, so we think we can maybe do better. So we're going to move the tables to InMemory OLTP. So again, we're dropping the table, recreating it as InMemory OLTP, and in this case we get a 25x improvement. And for sake of speed, I'm also going to change the stored procedures to memory optimized, and that affects the queries that run against the recommendation engine. Go back to the front page. Okay, so that's another 11x on top of the previous. Go back to this page and let's see what it takes. We now select a title. It's up 0.73 seconds, and buy another copy, 0.12 seconds. Way faster, much better user experience. And the Columnstore is just talking about how frequently can we afford to refresh your whole set of recommendations there. And that's going to refresh the recommendations on the base page there. Takes a couple seconds for that to kick in. Oh yeah, now it's down to 0.3 minutes. The payback for that is users are going to see real-time these recommendations updated to what are most of interest to them. So with that, open for questions. Thanks for your time. I hope this was fun.
Hey, Kevin, can you hear me?
Yes.
Okay, I'm sorry. Yeah, there was a little pause there. Hey, man, love that final demo. That was pretty, I mean, that was awesome. Let's get straight to the questions because we don't have a lot of time. So the first question was, what happened or did anything happen with the buffer pool? Did the buffer pool change because of InMemory OLTP?
The buffer pool hasn't changed as a result of InMemory OLTP. The only impact is that it has to share memory with the memory allocated to memory optimized tables. And we're integrating the resource governor to allow you to control the amount of memory consumed by in-memory tables to make sure that you still have room for buffer pool operations if you're tight on memory.
Okay. And what is the SQL 2014 official release date?
I believe we are declaring RTM tomorrow, and the general availability will be in April.
All right. And the SQL, and I'm sorry for going through these quick. I just want to make sure we get through as many as we can. But so has an announcement been made on which editions of SQL InMemory OLTP will be available in?
InMemory
Enterprise?
Yes, it will be an enterprise feature.
Okay.
So the additions to standard, again, are the buffer pool extensions and the increase in memory consumption, or the memory availability.
All right. And are there any kind of DMVs or views available for in-memory analysis?
We have lots of DMVs. So we worked hand in hand with CSS through the whole design process to make sure that we were going to have all the diagnostics. We also had a number of real-world customers working with us through early stages of the project. So we have a lot of diagnostics to let you understand what memory is being used, where it is, which tables are taking up how much memory, how much you've got left over, how up to date the threads that clean up old rows are. So yeah, we got you covered.
Awesome. Let's see. And then we had a few questions about the bucket count values. How did you calculate those values?
So bucket count ideally is 1 to 2 times the expected maximum number of unique key values. So if you have an index, which is 3 columns, how many combinations of those 3 columns do you expect there to be in production? So if it's a unique key, then how many rows do you expect there to be in the table? And you want ideally 1 to 2 times that maximum. If you end up with too small number of buckets, then when you follow that pointer, it's going to lead to a chain of all the rows that hash to the same bucket, and you're going to go through that chain to find your row. It functions. It's just going to be a little bit slower.
Okay. And so what happens if the server crashes or gets rebooted? Can you talk a little bit about what happens to the in-memory tables?
So we talked about how the in-memory tables, the updates are logged to the transaction log immediately,
Right.
and then they're copied off to the set of sequential files. When the server comes back up, we go through those sequential files and read those rows into memory and replace them, so when the database comes online, all of your data is right there just as it was as of the time that the server went down.
Okay.
Unless you've declared the table to be non-durable, in which case you intended it for it to not be there.
All right. Lots of questions.
Excellent.
Let's see. So do you see or foresee that Microsoft will have to raise or will raise the max memory limit in Windows Server 2012 above 4 terabytes since some of the new processors will support 6? There's a lot of memory questions. I'm trying to
Right. So again, with 2014, the amount of memory that can be used by in-memory tables for a database is limited to 256 gigabytes. That will change in future releases, but that's the cap for this release. Yes, we're constantly adjusting how much we can use based on the newer hardware that comes out. That applies to both the number of cores that we can leverage as well as the amount of memory. I don't, at this point in time, have at my fingertips what the current cap is for 2014. But yeah, that's always being raised.
All right. So what are the best practices in 2014 for DBA's configuration for, say, the max server memory? I mean, are there?
Well, SQL wants all the memory in the world. You know that.
Right.
That hasn't changed.
I think we're at about 4 or 5 minutes after. I think we at least touched on most of the questions. And you know, in about a week, we're going to have the archive of this presentation up on the website. And if there are any additional questions that we're not able to get to because of time, people are always welcome to email us, and we certainly try to be responsive to as many people as we can. Kevin, I want to thank you for the presentation. It was really fantastic. I enjoy it. I know that the InMemory OLTP is one of the most exciting. People are waiting, I guess. No, I mean, it's awesome. I mean, it makes a DBA like me pretty excited, actually.
Do remember the caveats about there's some queries that it works really good with and some queries that it's not so good. It's not the magic go fast button, but when you've got the right scenario, it is.
No, absolutely. I really want to thank you, Kevin. I'd like to thank you. I'd like to thank Microsoft. I'd like to thank Professional Association of SQL Server for allowing, the DBA Fundamentals Virtual Chapter the opportunity to share this meeting with our group. I'd also like to thank the users today. It's definitely the attendance and support that everyone gives us that's made this virtual chapter a success so far. I encourage everybody to visit sqlpass.org for information about the remaining presentations in this series. This is not today's meeting was not the only one. So, visit the SQL Pass website. I mean, it's a 14-part Microsoft series, so it's awesome. So, like I said, in about a week, today's recorded session will be available at fundamentals.sqlpass.org. You can rewatch it, you can pause it, you can do whatever you need to do to watch the parts of the session again that you need to. Again, great job, Kevin. I really enjoyed it, and I just hope everyone has a wonderful, wonderful day. Appreciate it.